Last time we were developing the Bose-Einstein distribution, we defined a grand canonical ensemble, a script Z, and then we were taking derivatives now. And so to pick up where we left off, we found that log of the grand canonical partition function, grand partition function is this expression here. That means that the log of z is equal to alpha n minus that expression. And so we can say then that dn prime of log of z of n prime minus alpha n prime is equal to d log z of n dn minus alpha. Of course, that's going to be equal to 0. So we can say the following: alpha plus the quantity n plus d log grand partition function d alpha times d alpha dn minus alpha is equal to 0. Or, take it a step further, n minus sum e to the minus alpha minus beta e sub s divided by 1 minus e to the minus alpha minus beta e sub s is equal to 0. That means that n is equal to sum over r 1 over 1 minus e to the minus beta e sub s, e sub r, sorry, e sub r. N sub s then is equal to minus 1 over beta d log z dE, and that's going to be equal to minus 1 over beta minus beta e to the minus alpha minus beta e sub s divided by 1 minus e to the minus alpha minus beta e sub s plus d log z d alpha e sub s. But because d log z d alpha is 0, the second term up here vanishes, and we're left with n sub s is equal to 1 over e to the minus alpha minus beta e sub s minus 1. And this, of course, as we did earlier, is the Bose-Einstein distribution. Furthermore, again, go through the same argument, and we're going to find that alpha is equal to minus beta times mu, where mu is the chemical potential, once again. Lastly, let's do this again for Fermi-Dirac statistics. Same method, but this time we have to only sum over two values, n equals 0 and n equals 1. Do it the same way as in the Bose-Einstein case. My grand partition function is sum over n1, n2, and so on, e to the minus beta times n1 e1 plus n2 e2 plus all the way up. Of course, my grand partition function, again, to remind you, is written as sum over n prime z of n prime e to the minus alpha n. Now, as we did before, I can write this then as sum n 1 equals 0 to 1 e to the minus alpha plus beta e1, sum n2 equals 0 to 1 e to the minus alpha plus beta e2, and so on up the line. Thus, log z log of my grand partition function is sum over r log of 1 plus e to the minus alpha minus beta e sub r. And therefore, log of my regular partition function z, non-script z is alpha n plus sum over r log 1 plus e to the minus beta, minus alpha minus beta e sub r. Same idea. Ultimately, n sub s is going to be equal to minus 1 over beta e log z e sub s, which is equal to 1 over e to the alpha plus beta e sub s plus 1. See? Plus 1 case here, minus 1 in the case of Bose-Einstein statistics. And of course, mu, the chemical potential, is equal to minus kT, or alpha. Beta mu is equal to alpha. Minus beta mu is equal to alpha. Wow, that's a lot of work. Let's look at what happens to quantum statistics in the classical limit. That's kind of an interesting venture. And I think that the results may surprise you, but then again, maybe not. You may have been expecting this all along, ever since I used the words Gibbs paradox. Let's see. Classical limit, n sub r is equal to 1 over e to the alpha plus beta e sub r plus or minus 1, where plus, of course, indicates Fermi-Dirac, minus is equal to Bose-Einstein. If the number of particles is fixed, that means that if I sum over r n sub r, that's going to be equal to n, of course. And I'll use this to determine alpha. My partition function, log z, is going to be equal to alpha n plus or minus sum over r log of 1 plus or minus e to the minus alpha minus beta e sub r. Now, let's look at the limiting cases. Suppose, so for limiting cases, because we're going to want to go, as I say, to the classical limit. What does that mean? There are a number of ways we can look at that. First, let's look at the case when n is small. What does that mean? That means we have a low concentration, so an ideal gas with a low concentration of the ideal gas. That means that all of the n sub r are much, much less than 1. And that means we don't have many particles in any one state or any of the states. What that means is e to the alpha plus beta e sub r is going to be, I should say, e to the minus is going to be much, much greater than 1 for all r. Secondly, suppose n is fixed, but we're at high temperature. So we're at high temperatures. That means small betas. In that case, only terms with beta e sub r much, much less than alpha are going to be large. Okay? So that means as beta approaches 0, an increasing number of terms with large values of e sub r will contribute quite a lot to the sum. But in order to keep n constant, alpha must become large as well to keep each term small. So at high temperature, or small n, we expect e to the alpha plus beta e sub r to be much, much greater than 1. And therefore, n sub r will be much, much less than 1 for all r. These are what we call the classical limits. High temperatures, low concentrations. So what happens in that case is both the Fermi-Dirac and the Bose-Einstein expression reduced to the same value. In other words, n sub r will reduce to n e to the minus beta e sub r divided by sum over r e to the minus beta e sub. Now this should look familiar. Looks a lot like Boltzmann statistics. Gets a little bit more interesting. Let's examine the partition function and expand the logarithm. So, log z is equal to alpha n plus or minus sum over r e to the minus alpha minus beta e sub r, which I can write as alpha n plus n. But alpha is equal to minus log n plus log sum over r e to the minus beta e sub r. Which means log z, then, if I put these two together, is equal to minus n log n plus n log e to the minus beta e sub r, sum over r. Hey, this isn't equal to the log of z for the Maxwell-Boltzmann distribution we did earlier. Not in Boltzmann statistics. Or I should say yes. But note, log z. I can write this as log z is equal to log of z from the Maxwell-Boltzmann, and this is Stirling's approximation for the log of n factorial. That is to say, and here's the punchline, z is equal to our old Maxwell-Boltzmann divided by n factorial. The factor n factorial is a natural consequence of this theory, of taking, in other words, deriving the quantum distribution functions, taking the limit as to let us go to low concentrations and high temperatures, so we're at a classical limit. If we evaluate the distribution function that results, it's not exactly the earlier Maxwell distribution. It's z divided by n factorial. Remember when we had the Gibbs paradox in the last unit, we said, well, the reason is we overcounted, so we have to stick in this value of n factorial. In this case, the n factorial comes about naturally. There is no ad hoc sticking in n factorial. And so there really never was a Gibbs paradox. It's just that we used the wrong paradigm to analyze the situation. In the case where we are in the classical limit, sometimes we call this gas non-degenerate. In the case when we're at low temperatures or high concentrations, and we have to use quantum statistics, either Bose-Einstein or Fermi-Dirac, we call that gas a degenerate gas. Now this is a real problem. This word degenerate and degeneracy is used all over physics, and it seems that every time you use it, you mean a different thing. And you can almost not be blamed for thinking that. Nonetheless, we will try to be very specific when we use the term degenerate. When we talk about a degenerate Bose gas or a degenerate Fermi gas, we're talking about a gas at low temperatures where you absolutely must use those statistics, and you cannot get away with classical statistics. I want to explore one more item before we go to a host of applications in Fermi-Dirac, Bose-Einstein, and then ultimately photon statistics. We're going to look at the quantum states of a single particle. So throw a little quantum mechanics back into this again. Suppose I have a particle of mass m, position vector r, momentum p, contained in a volume v, but it has no force. So it's essentially a free particle. I can write the wave function for that particle as some amplitude times e to the minus I times, we use kappa dot r minus omega t. And I can write that as a space part of the wave function times a time-independent part of the wave function times the time dependence e to the minus I omega t. Energy, of course, we can write as h bar omega. Momentum I can write as h bar times kappa, the wave vector. So I can write my energy then as h bar squared kappa squared over 2m. H bar, of course, is h over 2 pi. This comes from solving the Schrödinger equation for the free particle. That is to say, I h bar d psi dt is equal to a Hamiltonian times psi, where the Hamiltonian in this case is p squared over 2m, which I can write as minus h bar squared del squared over 2m for a free particle. Now, if I express psi of r and t in terms of the product of the two, the time-independent product times e to the minus I omega t, I get the time-independent Schrödinger equation, where I have del squared psi of r plus 2me over h bar squared times psi of r is equal to 0. Now, of course, in this case, we know this is a particle in a box. You've solved this in modern physics, and of course, you'll do it again in spades in quantum mechanics. But I can write this solution as psi is equal to a times e to the I k dot r. These are plane wave solutions to the particle in the box. You might remember that. And we know that minus kx squared plus ky squared plus kz squared plus 2me over h bar squared is 0. So, of course, my energy then looks like h bar squared kappa squared vector over 2m. But I'm going to apply the following boundary conditions. I'm going to apply periodic boundary conditions, which is to say that psi of x, y, and z is equal to psi of x plus L sub x, y, and z is equal to psi x, y plus L sub y, z, and is equal to psi of x, y, z plus L, z. So these are called periodic boundary conditions. Like you might see in a solid, for example. But what I want to do is apply these periodic wave functions, this solution, to a situation where we've confined the gas to a volume that's a parallelepiped of sides Lx, Ly, and Lz. So we can say that we have a volume equal to the product Lx, Ly, and Lz. Now, in order to use psi of r equal to ae to the I k dot r, in other words, my plane wave solution, the wave has to propagate indefinitely without any reflections or anything else suffered at the boundaries, which means that it must be the case that these conditions will apply. In order for that to be true, though, the following has to be the case. Kappa of x plus Lx must be equal to kappa x times x plus 2 pi n sub x, where nx is some integer. And of course, the same has to be the case for Ly and for Lz. So in other words, it has to be that, in this case, kappa x must be equal to 2 pi nx over Lx. Kappa y must be equal to 2 pi ny over Ly. Kappa z must be equal to 2 pi nz over Lz. if those are the conditions on kappa, what's the energy? Well, the energy, it's h bar squared kappa squared over 2m. I can write as h bar squared over 2m times kappa x squared plus kappa y squared plus kappa z squared, which I can write as 2 pi squared h bar squared over m and x squared over lx squared plus ny squared over ly squared plus nz squared over lz squared. Okay, so for given values of ky and kz, the number of possible integers delta n sub x, for which kx lies between kx and dkx, is delta n sub x can be lx over 2 pi d kappa x. I can extend this to 3 dimensions. Same thing is going to be true for delta ny and delta nz. Ly over 2 pi d kappa y, lz over 2 pi d kappa z. Totally, then we can say the product of the 3, let's write this over here. Delta nx, delta ny, delta nz then is just lx, ly, lz divided by 2 pi quantity cubed, d kappa x, d kappa y, d kappa z. Lx, ly, lz, all right, is a volume, d3 kappa divided by 2 pi cubed. This is what we call the density of states. G of kappa, d3 kappa. So this is what we call a density of states. We'll use this quite a lot as we go further in this. The number of states per unit volume with wave vector kappa is constant, and it's independent of the size or the shape of the volume. We'll come back to this as we go deeper. Let's evaluate the partition function in the classical limit. I can write this as n log of my single particle partition function, zeta minus log n plus 1. My single particle partition function is defined as sum over r e to the minus beta e sub r, which is to say, of course, that z is equal to zeta to the n over n factorial. But I can write zeta as sum over kappa x, kappa y, kappa z, e to the minus beta h bar squared over 2m, kappa x squared plus kappa y squared plus kappa z squared. Or I could separate them all and write zeta as sum over kappa x, e to the minus beta squared h bar squared, kappa x squared over 2m, sum over kappa y, e to the minus beta squared h bar squared, kappa sub y squared over 2m, times, of course, for the z, kappa sub z, e to the minus beta squared h bar squared, kappa sub z squared over 2m as well. But delta kappa sub z and delta kappa sub x, delta kappa sub, are going to be very, very small. I can replace the sums by integrals. And so I can write this instead as minus the integral, minus infinity to infinity, e to the minus beta h bar squared over 2m kappa x squared. By the way, these betas should not be squared, sorry. Times Lx over 2 pi d kappa x, Ly over 2 pi d kappa y, Lz over 2 pi d kappa z. And so when I do that, if I evaluate this integral, I'm going to get that I'll get Lx over 2 pi h bar times 2 pi m over beta to the 1/2. So you can look in the back at the tabulated value for that integral. In 3 dimensions then, when we do it for each of the integrals, I'll get a total, a single particle partition function of v over 2 pi h bar all cubed, 2 pi m over beta to the 3/2, which I can write as v over h bar cubed, 2 pi m kt to the 3/2. And this is what we found back in our earlier classical work. I can find log z. From that I can find my energy. My mean energy will turn out to be 3/2 nkt.
5 seconds.
My mean entropy will be k log z plus